Hello, my name is Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering at the University of Calgary. And this is Module 4 in our Circuits 2 lecture series, where I talk about the transient and steady state responses of circuits. Now, this is sort of your introduction into a very broad area in electrical engineering. And so when we talk about transient and steady state circuit response, we're basically going to be characterizing how a circuit behaves to sudden disturbances. Okay, so in your first circuits class, you would have looked at sort of constant sort of DC voltage level analysis, kind of like the stuff that we've been doing in our review earlier modules so far. You know, we apply a voltage of 5 volts and there's resistances of certain values, what are the voltages at those intermediate nodes. And when we do that kind of analysis, we sort of assume that that circuit has just been like that forever. That 5 volts has been there forever, the current flowing through those resistors have been there forever, and nothing, you know, it's always been that way. Same thing with the sinusoidal AC analysis that you would have been introduced to in your first circuits course as well. When you look at a sinusoidal voltage across a capacitor, you assume that that sinusoidal voltage has always been there and you're looking at it from that kind of steady state perspective. What we're going to be looking at here is what happens when you suddenly switch something on, basically. So what happens when you've got a circuit that is completely dead, there's no current flowing through it at all, and all of a sudden you throw a switch and you apply voltage to this thing instantaneously. As we're going to see, there's going to be sort of two responses or two behaviors that we're going to characterize in the circuit. One is the steady state response, which is where the circuit gets to after, you know, a large amount of time. And the second response is what we call the transient response, which is how that circuit behaves immediately after it's switched on. And this notion of transient and steady state responses is going to be a theme that's going to be picked up in other courses that you take in engineering. So for example, when you look at control systems, you have let's say a drone is flying through the air and it's, you know, on a nice path, everything is very steady, and it gets hit by a wind gust. Well, that wind gust is represented as a sudden disturbance to your system, and you're going to have sort of a steady state response once your control system figures out what to do, but you're also going to have a little bit of a transient response that characterizes what happens to the drone while it's reacting to that disturbance. Maybe the drone sort of, you know, wiggles back and forth in the air, and then it sort of straightens out again after it figures out how to compensate for that wind. And so just to be more specific, that's kind of a general introduction, but just to be more specific, I'm going to introduce you to this topic by looking at what happens when we switch on a simple circuit that consists of a capacitance in parallel with, a capacitance in series with a resistance. And so let's look at the following circuit where we've got some voltage source. And we have a switch. And this switch is going to be closed at time t equal to 0. We then have a resistance and a capacitance. The bottom portion of the circuit is connected to ground. We've got some capacitance C, some resistance R, and I'm interested in the voltage across the capacitor. Let's call this VO, maybe for the output voltage. Now, as we're going to see, once we get into this transient and steady state response stuff, and we start to get some analytical tools in our toolbox, we're going to see that the behavior of this output voltage, let's call it, looks something like this. So we've got the output voltage, VO, plotted versus time, and I'm going to draw Vs. up here on our y-axis, which is the value of our voltage source. So this is a DC voltage source. This is a constant voltage. And I'm just going to draw it as a dotted line here. Now, what we're going to find is that when we throw this switch and we apply a voltage to this circuit, we assume that no current is flowing through the circuit before the switch is closed. And so the voltage across our capacitor at time 0 is equal to 0. Once we throw that switch, we're going to find that the voltage can't instantaneously change. It's not going to immediately jump up. Instead, it's going to have this sort of gradual exponential increase to the point where it asymptotically approaches our source voltage. And so we call this asymptotic value that our circuit approaches, we call this the steady state response. And this period where the voltage is climbing up to the steady state response, we refer to that as the transient response. And so I'll just write that down. I'll say that's the final values of our circuit's operating levels at t equal to infinity. And so our steady state response is basically what our circuit looks like after a huge amount of time has gone by. We'll define it as infinite here. In practical terms, it doesn't have to be an infinite amount of time, but it's just long enough for this sort of transient response to die out. And so for this example, our steady state response is when our output equals our source voltage. And just to define our transient response, and so I'm going to define transient response here as the slow climb of our circuit's voltage as it reaches the steady state operating point. Now, this is a very imprecise, non-mathematical, kind of hand-wavy definition. But basically, I just want you to get the idea that we've got some final operating value that eventually we get to, but we have some sort of transient response in the circuit as well that prevents us from immediately getting to our final operating point. It takes us a little bit of time to kind of climb up to our final output voltage value, and it's this slow climb that we refer to as the transient response. And we're going to come up with mathematical tools to very precisely characterize all this stuff, but just from an intuitive point of view, this is what we're going to be talking about in this module. So as we look at transient and steady state response for the first time, we're going to focus on the scenario where we have a sudden change to our circuit. And for us, The most common scenario would be you've got a circuit that is just getting switched on for the first time, as we've drawn in our example here. There was no voltage or current powering it, and all of a sudden you throw the switch and the circuit is energized. What happens? And so this sudden flicking of a switch, we're going to model using a special mathematical function called the step function. And step functions, you're going to see these fairly often in your engineering education and perhaps in your careers as well. A step function is typically used to model a sudden disturbance. And so you see it quite often when you're modeling control systems. You've designed some control system to control the flight of a drone or the temperature in a refinery vessel. And all of a sudden there's a sudden disturbance. You experience a wind gust, or the fluid going into your vessel is suddenly stopped, or it's increased, or you experience some kind of temperature shock. And these are all typically modeled by sudden changes, which we represent using a step function. And the most basic form of the step function is something that we call the unit step function. And if I were to draw the unit step function, it's basically a waveform that changes as a function of time. And it's 0 until we hit time t0, and then it jumps up to 1. And so I'll try to draw this by a slightly thicker line. So this is what the waveform would look like on a graph. We can also represent it as an equation. Typically, we represent the unit step function by the lowercase letter u. And the equation looks something like this. We say that the unit step function is equal to 0 for, for negative time values, and it's equal to 1 for time values greater than or equal to 0. And so what I want to do as a first step to analyzing transient and steady-state circuit responses is to model our sort of switching on of a voltage source in terms of this unit step function. And so let's draw a circuit where, again, we have our voltage supply, Vs, and we've got a switch. I'm going to draw the switch a little bit differently than I did at the top of the page, just to make it very clear that our voltage is 0 before we throw the switch, or the voltage in our circuit is 0 before we throw the switch. At some time t0, so this is not, at time 0, at some time t0, we're going to throw this switch. This is our resistance. This is our capacitance. And at some time t is equal to t0, we're going to throw the switch. And we're going to go from having 0 volts across here to having our DC voltage source Vs. And so what I want to do is I want to basically take the voltage across these 2 points. I'm going to define it as Vi. And I'm selecting I because I'm going to consider this as kind of the input to our circuit. And we're going to talk a lot more about sort of the inputs and outputs of circuits as we kind of take a more systems view on how circuit design works. But for now, let's just define the voltage across here as V in. Our voltage of interest is the voltage across the capacitor. Let's define that as our output voltage. And basically what I want to do is I want to take this picture of this voltage source. We've got a mechanical switch and we've got a DC supply and all that kind of stuff. Not really maybe super friendly for mathematical analysis. And I want to basically represent this as an equivalent circuit where, we've still got our resistor, we've still got our capacitor, we've still got our output voltage, capacitor, resistor, but I want to get rid of all this kind of hardware here, and I just want to represent the voltage across here as this input voltage waveform. So this switching on of the source, I just want to represent as simply a voltage waveform VI, and I want to write VI in terms of our unit step function. That's basically where we're going. And so I don't think it's any kind of big mystery what VI is going to look like. If we just draw VI as a function of time, we've got some voltage level Vs. That's our source voltage. And then at some time t naught, we go from having our switch connected to ground to switching it over to be connected to the voltage source. And so this is what our input waveform looks like. Instantly at time t0, we go from a voltage of 0 to a voltage at Vs. And you might say, well, wait a minute, we just said that voltages can't change instantly, or I suggested at least voltages can't change instantly. But remember, this is our input voltage. So the input voltage, we're suddenly changing instantly, and it's that output voltage that's going to be a little bit lazy and slow and won't immediately respond due to the capacitor. And we'll see mathematically why that ends up being the case later on. So, but to get there, the first step is I want to construct this waveform, or express this waveform in terms of our unit step function. And so our unit step function, if you remember, looks like this. And so it, at time 0, jumps up to a level of 1. And so I'll just try to make that a little darker. And so this is kind of a problem, right? Because, well, there's two problems. One is Vs is probably not equal to exactly 1 volt. It might be bigger or smaller. The unit step function is only equal to 1. Also, our voltage source doesn't switch on until time t naught, and the unit step function always has to jump up at time t equal to 0. And so we can make a few modifications here. So I guess maybe step 1, scale the unit step function. And so V input t, and I'll just put a prime here because we're not quite where we want to be, but let's say our V input prime is equal to our source value Vs multiplied by our unit step function. The nice thing about the unit step function, because it is equal to 1, if we want it to take on any other value, we just multiply it by that value. It's super easy to scale. And so this waveform would have a value of Vs, but it still switches on at 0, right? So the last thing we need to do is shift the waveform so it switches on at the right time. So step 2, so our actual input voltage waveform is equal to our scaled version of our unit step function. Whoops. Shifted by t naught seconds. And so when you shift this, you get this exact waveform, but it's shifted over to the right so that it switches on at time t naught. Probably you've seen this kind of time shifting notation before, but how does it work exactly? Well, we know that our original waveform switches when it gets an argument of 0, right? So u is a function of time, and when that t value, or the input to that function, is equal to 0, then it switches up, right? And so at time t is equal to t0, whoops, yeah, exactly, no, that's fine. So if we plug in a value of t0 for time, we get Vs multiplied by our unit step function. That's equal to t0. Our shift value is equal to t0, and so we get Vs u of 0, and that, when the unit step function gets an argument of 0, that's when it switches on, basically. So you can experiment with this, try a value that's a little bit smaller than t0, a little bit bigger, and satisfy yourself that this works fine. But basically, this is our final expression when we want to represent our voltage source switching on at a certain time t0. If we want to express it in terms of our unit step function, this is what that equation looks like. Okay, so now we're ready to calculate something called the step response of our resistor capacitor circuit. So I've just redrew this same circuit that we had on the previous page, just because it's useful for us to be able to look at it right now. And so we're interested in figuring out the voltage across the capacitor, how the voltage across the capacitor changes as a function of time. This is called VO. As kind of, we can think of it as our output voltage. And our input voltage, VI, is basically this waveform up here, right? So we switch on our power supply at some time t0. And we're going to analyze this circuit using the same tools that we used for our resistor circuit analysis review. The first thing is that we're going to define the current through the resistor as IR, and then the current through the capacitor as IC. Now, by Kirchhoff's current law, we know that the current flowing through the resistor has to equal the current flowing through the capacitor. And so now what I'm going to do is I'm going to write the equations. I'm going to substitute in the equations for the current through the capacitor and the current through the resistor. And so the current through the capacitor is equal to the capacitance multiplied by the derivative of the voltage across the capacitance. And in this particular circuit, the voltage across the capacitance is our output voltage. And the current through our resistor is just given to us by Ohm's law. We know that V is equal to IR, and so current is just equal to the voltage across the resistor divided by the resistance. And in this case, the voltage across our resistor is our input voltage, which is the voltage at that point, minus our output voltage, the voltage at that point. And so we have Vs times our unit step function, t minus t0, minus our output voltage, divided by R. And I'm just going to group terms here, get the output on the left-hand side and then the source on the right-hand side. So we've got the derivative of our voltage plus our voltage divided by the resistance is equal to our source voltage multiplied by our delayed step function divided by RC. And then hopefully you can see what I've done here. I've just taken this output term, moved it to the left-hand side. I've divided everything by 1 over c, and I just sort of collect our terms here. Now, let's look at, like, we're really interested in looking at this circuit or figuring out what happens after we turn the switch on. And so let's just sort of look at our circuit for t values of time greater than or equal to t0. And for that, we can simplify our equation a little bit. So we know at t0 or greater, this unit step function is just equal to 1, right? And so the right-hand side of our equation is just Vs divided by Rc. And the output voltages are still a function, and Vs is a constant. The output voltages are still a function of time. I'm just going to drop this, the function of time, just to make our notation a little bit simpler. But just remember that the output voltages still are a function of time. And I'm just going to write the derivative of the output with respect to time plus the output voltage divided by Rc. And so this is our differential equation that we have defining our output voltage at time greater than or equal to t0. And so basically what I'm going to do is I'm going to solve this differential equation, and we're going to see how our voltage behaves as a function of time. So again, manipulating our equation a little bit, I'm going to isolate the derivative so it's by itself on the left-hand side of the equation. And this is just going to be equal to the negative of V0 minus Vs over Rc. I'm just going to put that negative in there. It makes our lives a little bit simpler later on during the derivation. And what I'm going to do is I'm then going to divide through by V0 over Vs and multiply through by dt. So I just took the numerator, dumped it down there, took the denominator dt and put it up there. And so this is the equation that results. And what I want to do now is I basically want to integrate both sides, because I don't want to have these dVs. I just want to figure out what regular old voltage is. And so I'm going to integrate. Oh, sorry, and this, that should be an uppercase Vs, because that's just our constant source voltage. Vs dV0 is equal to the integral of minus 1 over Rc dt. Okay, so that's fine. I just put integral signs in front of both the left-hand side and the right-hand side. But it's important also to put some upper and lower limits on our integration. And so for the right-hand side, this is reasonably easy or straightforward. So we basically want to figure out what happens to this circuit from the point that we switch it on to some time t that's a little bit later on after we've flicked that switch. And so we start our time integral at time t0, that's when we throw the switch. And then we integrate up to some other time t, and as we said on the previous page, t is some time that is after our switch on time, basically. Now, on the left-hand side of the equation, we're integrating with respect to voltage. And so we're expecting once we switch this circuit on that we're powering it up and voltage levels are going to basically increase in this circuit, because we assume that before we switch the circuit on that the input is connected to ground, right? So the voltages basically throughout the circuit are going to be 0. And so when we flick the switch at some time t0, our output voltage and all the voltages in our circuit, even though it's a fairly simple circuit, would be equal to 0. Now, we then are interested in figuring out what our voltage value, our output voltage value V naught is at some time t. And so our final value for our integral will be basically V naught t. And so we're integrating with respect to our output voltage. And so this is, you can almost think of it as kind of a placeholder. This is basically telling our equation, if you want, that we're integrating from our initial voltage, which is voltage 0, to some unknown final voltage at some time t. Okay? And so what we're going to do now is we're just going to sort of go through and apply our calculus and solve these two integrals, basically. So here's the solution for the time integral. The time integral is pretty straightforward. I apologize for my notation, though. I realized that I'm integrating with respect to t, and also my upper bound is also equal to t. That's kind of bad form. I probably should have changed the variable of integration to something like tau, for example, but I'll just leave it the way that it is, and hopefully you'll be able to follow along. So we integrate from t naught to t. This is basically a constant with respect to time, and so we end up, the antiderivative is equal to t, which is our variable of integration, over rc, and then this is our lower and upper bound. So we just substitute the values in here. So we substitute in t for t. Again, apologies for that. And then we substitute in t naught for t. And this is our answer, right? So this is the solution for our the right-hand side of our equation. The left-hand side, this voltage integral is a little bit trickier, and because we have to solve it using integration by parts. So here's the first part of our integration by parts. And again, sometimes in these videos I will just kind of pause the video and then write some stuff down, just so you don't have to stare at my hand kind of writing things across the paper. But again, if you need a little bit of extra time to copy it down in your notes, remember you can just pause the video and rewind. So this is our voltage integral. We're going to do, sorry, not integration by parts, but variable substitution. And so I don't like this V naught minus Vs. I would rather just have it be equal to 1 over U. And so I'm going to define the variable U as V naught minus Vs. When I take the derivative of the left-hand side, I get du. When I take the derivative of the right-hand side, I get dV naught minus, because Vs is constant, this ends up just being equal to 0. And so du is equal to dV naught. Now, whenever you do variable substitution in your integral, you also have to change your, or potentially change your the limits of your integration. So limits of integration, our lower limit is 0. So we have, and when we say this is 0, it's kind of like saying that we're starting our integral at V naught, like our output voltage, which we're integrating with respect to. We're starting our integral at V naught is equal to 0. And we know, and we have to express our integral now in terms of u. And so we basically take 0 and plug it into our equation for u. And so if V naught is equal to 0, u is equal to 0 minus Vs. Or in other words, just equal to minus Vs. So when we integrate with respect to u, we start our integral at a lower bound of negative Vs. Our upper bound is equal to just our unknown voltage at time t. And so that upper limit for our integral is then just our unknown voltage minus Vs. And so if we take this integral and we express it in terms of u, we now have the integral 1 over u dV naught is just equal to du, right? So that's nice and simple. Our lower bound for our integration is minus Vs. Our upper bound is V naught at time t. minus Vs. And we know that the antiderivative of 1 over u is just the natural log. And so we have the natural log of u from minus Vs to v naught of t minus Vs. And obviously that's just equal to the natural log of v naught of t minus Vs minus natural log of negative Vs. And so when we take this solution and we combine it with this solution, our overall equation is the solution for this integral, which is this value, equal to the solution for this integral, which is this equation. Okay, so now that's a lot of natural logs. We want to get rid of those natural logs. And so to do that, I'm going to take advantage of a property of natural logs. And if we have the natural log of some value a minus the natural log of some value b, that's the same thing as the natural log of a divided by b. And you can, you might find that in one of your calculus textbooks, or you can easily check it on your calculator to make sure that that actually works, satisfy yourself that that works. And so using that using that identity, we have the natural log of v naught of t minus Vs over negative Vs is equal to minus t naught divided by RC. And so what I'm going to do next is I'm going to take the exponent of each sides of this equation. And so I'm going to take the exponent, I'm going to pass the left-hand side into the exponent function, and I'm going to cheat a little bit here. And I'm going to pass the right-hand side into the exponent function. Of course, the exponent and the natural log functions are inverses of each other, and so these two just cancel out. And so we have v naught of t minus Vs over minus Vs. And this side I'm going to write as, we can write the exponent function as exp, or maybe a slightly more elegant way is just e to the exponent of t minus t naught over Rc. Or if we, and then just kind of rearranging our terms here, we finally have our results. So our unknown voltage at some time t is equal to our source voltage minus our source voltage multiplied by this exponent term, t minus t naught over Rc. And so this is it. This is our step response to our RC circuit. So when we turn our switch on at some time t naught, this is the equation that defines what our output voltage looks like. And I'm going to draw this and talk about it in a little bit more detail in a second, but just a few words. Remember, this is valid only for t greater than or equal to t naught. So if you plug in, let's say t naught is 1 second, you can use this equation to figure out the output voltage for any value of t greater than or equal to 1 second. However, it doesn't work for values less than a second. If you plug that in, then you get all kinds of weird results. If you want to know what our output voltage is at time t less than t naught, It's just 0, right? Because before T naught, our circuit was off, its input voltage was connected to 0, and we assumed that our output voltage was equal to 0 as well. We actually rolled that into our equation when we were solving this differential equation. And so I guess if you want to be like quite complete about it, we would write our final expression for the output of our circuit as So the really nice thing about this equation is that it very clearly separates into the steady state portion of the response and the transient portion of the circuit response. And so if you remember, when we drew a picture of our output voltage, we had some value Vs, and let's let this be T naught. So before T naught, and then this is a function of time, before we flick the switch at time T naught, our output is 0. After we flick the switch, it slowly increases to some value Vs. And so we can see this now in our equation. Our equation is equal to Vs minus Vs times e to the minus T naught over Rc. So this term is the steady state response. This is the constant value of Vs that eventually our circuit climbs up to. This portion of the equation is the transient response. Now the transient response, when right after we switch on, or right after we throw our switch, so when t is equal to t0, our output is equal to Vs minus Vs, e to the minus T naught minus T naught over Rc, which is equal to Vs minus Vs e to the 0. And this, of course, is e to the 0 is equal to 1. So we end up getting Vs minus Vs, or 0. So, and this should be T0 also. So at time T0, the output of our circuit is equal to 0. We can't have an instantaneous change of voltage across a capacitor. And so our transient term basically takes our steady state term and pulls it right down to 0. It doesn't let it change at all. Now, after a very long time, let's say t is equal to infinity, we have Vs minus Vs e to the minus infinity minus T naught over Rc. Well, when you take an exponent to a very large negative value, the exponent basically decays to 0. And so this ends up being Vs minus 0, or Vs. And basically this kind of highlights the behavior or the nature of transient responses. Transient responses decay to 0, and the steady state responses stick around, basically. And that's what causes sort of our increase to that final value of Vs. And then just finally a little bit of notation. When we are dealing with RC circuits, we often talk about something called the time constant of the circuit, right? And the time constant is just basically the product of the resistance times the capacitance. And we often represent it using a tau. So tau is equal to Rc. And so our output voltage let's say the transient component of our output voltage is Vs. Actually, it's negative Vs technically. T minus T naught over RC. And so we just sometimes you'll see people substitute in the value tau for RC. Oops, yeah, exactly. And basically, the larger your time constant, the longer it takes for your transient response to go away, the longer it takes for it to disappear. So a circuit with a very short time constant will very quickly rise up to its steady state value. So tau is equal to something small. Vs. The response might look something like this, very quick. And if your time constant is something very large, then it might take a long time to approach Vs. And in fact, you can kind of, there's a little bit of a rule of thumb for estimating time constant. And the time constant is basically how long it takes for the transient response to reach roughly a third of its final value. And the reason for that is, let's say we let our t minus t naught argument, well, let's let that be equal to tau. And so our transient response is minus Vs e to the minus tau over tau, right? If we let our numerator equal our denominator, which is equal to minus Vs times e to the minus 1, which is equal to minus Vs times 0.368, right? And so basically one value of tau is, if you find the approximately 1/3 point on your transient response and you go over and you find its location on the x-axis, that's roughly where tau is. So if you're looking at the waveform of a transient response, whether you've created a circuit and you've measured it or you're simulating it, you can kind of just eyeball the voltage waveform and say, okay, yeah, we're at about a third, and that's roughly where the time constant for our circuit is.